All right, welcome back. So today we are going to be continuing on with kind of our second section inside of our equilibrium unit, and this is focusing on acid and bases. But first of all, before we even get to that, we are going to look at something called the water ionization, so what that is, and then we're going to look at some kind of a repeat of old Chem 20 stuff, and we're going to look at how to calculate acid and base strength. So of course with water, and we kind of looked at this in Chem 20 when we were there, is that we know that water can undergo an auto-ionization. So what that means is that water will spontaneously form very low concentrations of hydronium, H3O+, and hydroxide. And of course this happens when two water molecules, so about 1 in every 2 in 1 billion, will actually collide and transfer a hydrogen ion. So of course this is what we kind of have like here, actually representing it. We got two water molecules. We can get a transfer of a hydrogen ion, which remember is H+. That is how we can get hydronium and hydroxide being formed. So of course if we wanted to do equilibrium calculations with it, we can write out the equilibrium law to look something like this. And of course, this is why pure water has a very slight conductivity, and it's only detected by very sensitive instruments. So I have right here, so only 2 molecules in every 1 billion would actually ionize. So the equilibrium greatly favors the formation of water, or the reactants. So we can expect an equilibrium constant that is very, very, very low, so very largely below 0. So of course, if we want to take our equilibrium that's written up here and write out the equilibrium law, what we can do is we can write Kc. Now that's normally equilibrium law, but because we're dealing with water and water is not going to change, what we're going to do is take out the C and write Kw. Now K, this is still equilibrium, but the reason we're using W, just means it's specifically for water. Now of course remember, when equilibrium, it's products over reactants, so our products are H3O+ raised to the power of 1, because the molar coefficient is 1 in front, times hydroxide, also to the power of 1, all over. Well, we're going to leave out water because, remember, H2O is a liquid and is removed from the equilibrium constant. So what we are left with, and I have this down for you guys right here, Kw, or equilibrium constant, is just going to be the concentration of hydronium times hydroxide, which is going to give you the value. It's 1.0 times 10 to the power negative 14. So that's why this number is very, 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 very small. So that's why it mostly favors the formation of our products. Now this is also found, formation of our reactants. Now this is also found on page 3 of your data booklets right here. So this is always going to be given to you. Now the reason we kind of need this, like this Kw, or the ionization constant of water, is going to show up a lot. But using this whole idea as well, we can actually use this to find the concentration of our ions in neutral water, so at a pH of 7. So if we did out our ice tables, something like this. Now we know water we can leave out because it is a liquid. It's not going to count our equilibrium expression. Hydronium and hydroxide are first going to start off with 0 because that's what happens initially. Now how they're going to change, we're going to get a plus X and a plus X. So at equilibrium, their concentrations are both going to be X. So if we did out a little bit of math, so Kw is equal concentration of hydronium times hydroxide, we can get 1.0 times 10 to the negative 14 is equal to X times X. So 1.0 times 10 to the negative 14 is equal to X squared. So we take the square root of both sides, and we get X is equal to 1.0 times 10 to the negative 7. So that's how we can say at pure neutral water, the concentration of hydronium and hydroxide are equal to each other, and it is 1.0 times 10 to the power negative 7. So this, of course, is handy to kind of keep in mind, is because as we know with water there, the concentration of hydronium and hydroxide are always going to be related to each other. So what that means is that we can actually take our equation, or the previous one, because it has both hydronium and hydroxide in it, and depending on whatever concentration or whatever kind of solution we have, if we manipulate our equation to solve for hydronium, we get Kw over concentration of hydroxide. So in this scenario right here, if we're given a concentration of hydroxide, we can solve for hydronium, or we can solve for hydroxide if we're given hydronium. So this is going to be kind of a relationship between all acidic and basic and even neutral solutions, is that we have this relationship between hydroxide and hydronium and the ionization constant of water. So we can relate all these, and depending on what type of solution we're given, we can calculate anything we want. Now, this is just a reminder. We've seen this relationship before between hydronium and hydroxide when we had this equation. Because remember, we had the POH plus POH is equal to 14, where the POH was basically concentration of hydronium, and from our POH we can get hydroxide. So we've seen this relationship before. So this is just kind of breaking it down in a new term, is that we have hydronium and hydroxide directly linked to each other. So this is really nothing new, and we're going to see this formula show up again later. But first of all, we're going to just get some calculations, or just kind of looking at some of the stuff right here. So remember, if we're trying to solve for either hydronium or hydroxide, depending if we're given an acid or base. So remember, for our strong acids, the concentration of hydronium is equal to that of the strong acid. And for our strong acids, remember there are 6 strong acids. Now in Chem 20, you were to have those memorized. You don't need to have those memorized for Chem 30. So if you go to page 8 and 9 in your data booklets, you'll notice that we have the hydronium ion right here in gray. And if you count the number of acids above this, we have 1, 2, 3, 4, 5, 6. So actually right here in your data booklets, all the ones above the hydronium ion, these are our 6 strong acids right here. So you don't need to have them memorized. So what that means is that if you're given any of these here, so concentration per chloric acid, hydroiodic acid, hydrobromic, hydrochloric, or nitric, sulfuric is going to be a little different. So we're going to avoid sulfuric acid. Actually, Chem 20 avoids sulfuric acid. Chem 30 avoids sulfuric acid altogether, because it is a little more challenging to deal with. But for the most part, we have 5 out of the 6. As long as you have their concentration of the acid, that is going to be hydronium. Now later, so next week, we're going to be looking at weak acids. So basically our data booklet, everything below the hydronium ion here on page 8, and it continues into page 9, right? So there's a lot more weak acids, and that's going to be our next week stuff when we're going to look at that. Now for hydroxide, because all strong bases are ionic hydroxide, so they have a dissociation equation. So the concentration of hydroxide is equal to the concentration of the original base times the mole ratio from our dissociation equation. All right. So for example, we're going to get that one, right here when we do magnesium hydroxide, we'll kind of get to that. So let's look at our first example. So it says calculate the hydroxide ion concentration of a 0.250 moles per liter solution of hydrochloric acid. So hydrochloric acid is a strong acid. So therefore, concentration of H3O plus is equal to the concentration of HCl. So we get concentration of H3O plus is just equal to 0.250 moles per liter. So knowing that, if we want to get the concentration of hydroxide, right, we just go back and look at our equation from the previous page here. We get concentration of hydroxide is the ionization constant of water divided by the concentration of hydronium. So we are going to take Kw over concentration of hydronium. We get 1.0 times 10 to the negative 14 all over 0.250, and we get concentration of hydroxide is going to equal, you need to do this out, we get 4.00 times 10 to the negative 14 moles per liter. And that is how you do these right here. So you'll notice the next example is almost the exact same thing. Calculate the hydroxide ion concentration in a 0.350 moles per liter solution nitric acid. So following the steps just up above, in 3 seconds the answer is going to come up, but please pause the video and try this one. And when you do this one, you should get the concentration of hydroxide being 2.86 times 10 to the power of negative 14 moles per liter. So that's how we solve for the acid ones. Now, like I said, the base ones are going to be a little different. So I'm going to do example 3 with you, and then hopefully you can do example 4 on your own. So what we have right here is calculate the hydrogen ion, or hydronium is another way to say that, concentration in a 0.075 moles per liter solution of magnesium hydroxide. So of course, magnesium hydroxide, we know we have a strong base, but you have to pay attention to this little bit up here. So the concentration of hydroxide is equal to the concentration of the base times the mole ratio from our dissociation equation. So you will need to write a dissociation equation to figure out the mole ratio, where magnesium hydroxide is MgOH2. So this is going to dissociate into Mg2 plus and 2 hydroxide molecules. So we get the concentration of hydroxide is equal to the concentration of magnesium hydroxide times our mole ratio. So our mole ratio, remember, stoichiometry is wanted over given. So hydroxide is our wanted, magnesium hydroxide is our given. So we have 0.075 times 2 over 1. And we get the concentration of hydroxide in this case right here being 0.150 moles per liter. And from there, once you get that, we do what we done up above. So we use our equation. Concentration of hydronium is equal to Kw over concentration of hydroxide, and we get 1.0 times 10 to the negative 14 all over our 0.150. And when you solve this, we should get 6.7 times 10 to the negative 14 moles per liter when we solve. So this one is just a little different because we do need to have that mole ratio. So just remember the above there, just where you need to do that dissociation equation if you are given a base. And it's only the bases that are going to do this, and the reason for it is they are ionic. All the acids are molecular, whereas the bases, of course, are ionic, so that's why they have a dissociation, not an ionization. So example 4, this one is a little different. So let's calculate the hydronium, or the hydrogen ion concentration, in a solution prepared by dissolving 15 grams of sodium hydroxide in enough water to make 3 liters of this particular solution. So this one here, of course, is still a little different, where we're given a mass, but we've done this before where you can figure out concentration of bases if you're given a mass. So just for challenging purposes, I want you to pause the video and try this one, and the answer is going to go up in about 3 seconds. And hopefully when you go through the steps, you should get the answer down here that I have in the block. Now, I never showed this formula here, so concentration of hydronium is equal to Kw over hydroxide, just because of space, but I did want to show you the steps. So first of all, using the mass and molar mass, so this one right here, to get the number of moles, then using the number of moles to get the concentration of the ionic base, which is sodium hydroxide, and then using the equation above, so hydroxide is equal to the concentration of the base times our mole ratio, and finally solving. So of course these here, this is a lot of kind of Chem 20 review, but definitely it's just kind of make sure you remember these right here, specifically for our next few lessons. Now, before we jump into the pH and pOH calculations, as kind of a reminder, kind of have to go through what pH and pOH actually means, and of course, how they can help us determine concentration and stuff like that. So, of course, communicating concentrations using pH and pOH, of course, we are going to see our formulas again, but just for right now, just a quick little reminder of what pH means. So pH just means power of hydrogen, and it was developed for the wide range of hydronium ion concentrations. So this is where we use our log scale to narrow down the pH of hydronium and hydroxide between a scale of 0 and 14. Now, one thing you do have to be careful for as well, if you do see any questions like this show up, is a change in one pH unit is an increase or decrease in concentration by a factor of 10. So this means that if you change 2 pH units, the concentration will change by 100, or 10 squared. Right, so however how many pH units you change, you kind of put that to the power of 10. So if it changes by 5 pH units, then the concentration will change by 100,000, because 10 to the power of 5 is equal to 100,000. So how this is going to show up when we look at some examples right here. So how much would the hydronium ion concentration if there was change in 3 pH units? So the change, we go 10 to the power of 3, or 1,000. So a change by 1,000. Now, practicality-wise, if you see something like this, like the pH of Coke is 4, while pH of lemon is 1, how many times more acidic is the lemon than the Coke? So figure out how many changes in pH units. We go 4 minus 1 is equal to 3. So there was a change of 3 pH units. And we already did the math up above for that one. So that means a lemon is 1,000 times more acidic than the Coke. Now, of course, I know it's more acidic because, of course, when we have here, the Coke's at a pH of 4, lemon's at a pH of 1, so we're getting more into the, more acidic range. Whereas this one right here, ammonia has a cleaning solution has approximate pH of 10, while a laboratory solution of sodium hydroxide has a pH of 14. How many times more basic is sodium hydroxide? Obviously, this is higher, so it's more basic. So to figure out how many change in pH units, 14 minus 10 is equal to 4. So a change in 4 pH units. So that means we go 10 to the 4, and that is equal to 10,000. So we got the NaOH is 10,000 times more basic than the ammonia. And that is how we solve these practical problems like this if you are given those. So once again, just kind of keep this in the back of your mind. But if you kind of do the calculations that we're going to show you on the next page, then you can just actually use hard numbers and figure out how many times more acidic or basic something is. Alright, so once again, this is more of a Chem 20 review, but this is where we're definitely going to spend a little more time just on solving some of these problems, just because you will need to have these formulas kind of, not really memorized, but just know them, because right now we are definitely leaning towards everything's going to be in the acid and base section, so you can imagine there's going to see a lot of pH and pOH. So, and also just remember, pH pairs up with hydronium, and pOH pairs up with hydroxide. Okay? Now, if you're given an acid and it's asked for pOH or anything like that, you're either A, going to use this equation right here, so relating pH and pOH, or concentration of hydronium times concentration of hydroxide is equal to Kw. So these are two of these right here. These are your two formulas to relate pH and pOH, or hydronium and hydroxide. So this is where you have to read the question carefully, understand if you're given an acid or a base, and then have to look at what you're asking to solve for, which we'll kind of get into that when we get into our next few questions. Now, for significant digit wise, like I said, normally not going to worry too much about significant digits for this one right here, because if you were doing a diploma, everything's on Scantron anyway, so you can only have, however many significant digits they tell you. But for a pH and pOH, because it's on a log scale, the number of digits following the decimal point in the pH and pOH is equivalent to the number of significant digits. So what that means is that if you have a pH of 4.45, now normally if it was a concentration we count all the digits, but here we only look at following the decimal, so this is 2 significant digits. If we had a pH is equal to 1.1, well, this is only 1 significant digits. So for these right here, all my answers are gonna be a correct number of significant digits, and definitely try to do all your calculations with the correct number of significant digits, but like I said, wouldn't worry too much about it at this particular point in time. So using our above equations, we have a bunch of different examples that we're gonna go through. So some of them are going to be pretty straightforward, because when we start off example 1, we have find the pH of a solution where the concentration of hydronium is 2.5 times 10 to the power negative 11 moles per liter. We have pH and hydronium, two of these match, so it can go into the equation of pH is equal to negative log concentration of hydronium. So that is equal to negative log 2.5 times 10 to the power negative 11, and we end up getting an answer of 10.60. Now that's all I'm going to write, because we have 1, 2 significant digits in our concentration, so 1, 2 significant digits in our pH. Now, example 2 is a little different, because where it says find the pH, so pH, remember, pairs it with hydronium, but we're given hydroxide ion concentration. So because of this, there's 2 different ways you can solve. You can use the hydroxide ion concentration at pOH, and then use this equation right here to find the pH. That works. Or we can use this equation to find hydronium and then find the pH. Either way, both ways you'll end up getting the same answer. Just because we learned this equation just on the previous page, I'm going to start by doing this. To get the hydrogen ion concentration, or hydronium. And when we do this, we get 4.1. And repeating 6, I'm just going to keep as many digits as possible, times 10 to the power of negative 12. And then, because now we have hydronium, we can get the pH is equal to negative log concentration of hydronium. And we get negative log times 4.16666666, and it just repeats. And we end up getting 11.38. Once again, 2 significant digits. So that is if you are given something with a pH and you have the other thing that doesn't match, so hydronium. You just have to be careful about what the question is asking, what species you're given, and what is asking to find. So with that in mind, pause the video and try this one on your own. Example 3, where it says calculate the concentration of hydronium if the pH of the solution is 5.25. So just look up above, see if you can find the relevant equation and see if you get this answer. And we need to do this out, so hopefully you have the appropriate equation. So concentration of hydronium is 10 to the negative pH. So we go 10 to the power negative 5.25. So this is 2 significant digits. So my final answer, 5.6 times 10 to the power negative 6 moles per liter. All right. So 2 more just to go over, and I believe that is it for this particular lesson. So example 4, solution has a pH of 3. Calculate the pOH and the concentration of hydroxide. Now, of course, this one right here, it is kind of giving it away that you can calculate pOH first from the pH and get that, but this could easily be scratched out and just so you have pH and then try to find hydroxide. But either way, we can go about this many different ways, but of course, just because this lesson first, why don't you find the pOH first? So this is where we have the formula pH plus pOH is equal to 14.00. So pH is equal to 14.00, oh sorry, pOH. Is 14 minus pH, so pOH is 14.00 minus 3.00, and we have a pOH of 11.00. So that is finding the pOH. Now the fact that we have pOH, if we look back and look at your formulas for hydroxide, we have the concentration of hydroxide is 10 to the negative pOH. So if we have the pOH is 11.00, we get 1.0 times 10 to the power negative 11 moles per liter. And that is how we can solve ones like this as well. Now, the last one is definitely going to be a little more challenging. I definitely want you to try this one on your own, kind of using the steps that we outlined before. But I am going to give you a little start right here. It says calculate the pH. So remember, pH is power of hydronium, but we have 10.3 grams of calcium hydroxide, and this is a base. Okay, so we're asked for the pH, but we're given a base. So there's different ways that you can solve this one. Now think back to as well when we did our example back here, where because we have a base, we need to write a dissociation equation and solve. And actually this example right here, 4, kind of highlights all the steps that we need to do to find hydronium. And then with our example 5, we're just applying the pH calculation at the end. But huge thing right here where we already have everything listed out that we need to do. So, like I said, I want you to pause the video, give this one a try, and I'm going to have the answer up for this one in 3 seconds. And hopefully, something that looks like this. So we have first, of course, writing out our equation because we have CaOH2. So we write our dissociation equation because we know it is a base. Our first step, of course, find the number of moles of calcium hydroxide, doing mass over molar mass. To get the number of moles. Then we find the concentration of calcium hydroxide using the formula number of moles over volume. So you have to remember to convert the milliliters into liters to get the concentration of calcium hydroxide. Then our third step, using our concentration of the base to find the concentration of our hydroxide by going concentration of hydroxide is equal to the concentration of the base times our mole ratio. And our mole ratio, of course, wanted over given, so that's why it is 2/1. So that's our mole ratio right here. Then I used our formula that we learned at the beginning of this lesson to find the concentration of hydronium. So hydronium is Kw over concentration of hydroxide, and we get this particular number right here. And then of course all this because where we needed to get pH, we needed everything in hydronium. So as soon as we have the hydronium, we plug that into our equation of pH is equal to negative log concentration of hydronium, and we get 13.745 as our pH, which should make sense because if we have a strong base like calcium hydroxide, we should expect to have a very high pH, right? So if you're doing a question like this and you knew something was a base and you get a pH below 7, remember that's in the acidic range, you know that you've made mistakes in your calculation somewhere. So all your answers should kind of make sense as you're going through. Now this is by far kind of mostly review from Chem 20, right, where it is using our equations right here. So it's just kind of using our equations that I have listed right here. So the big thing is, of course, getting familiar with them. Inside of your workbook, there are a bunch of different questions around the pH and pOH where you're given either strong acid or bases and you're using either all of them or only some of these 6 equations right here that I have highlighted in your notes and the pH and pOH formulas. So please try them. And then of course next lesson, the that we're going to look at is we're going to look at a new acid-base concept, and then we're going to be looking at ways to predict acid and base reactions. And that'll be it for this week. So I'll see you guys for the next lesson.